Hello, my name is Kevin Walker, and along with Daniel Shirley and John Matz, this is our presentation on our audio amplifier. To finish ECEE352 analog electronics, and for us to understand the use of JFET, BJT, and amplifiers in general, a project to build an audio amplifier was done. It is made up of two major parts, a preamplifier and a power stage. This device will play music from a smart device, such as a smartphone or an iPod, and it will be played through a speaker. The goals of this project is that the amplifier will cover a frequency range of from 20 Hz to 20 kilohertz, and it must have an overall gain of between 200 volts per volt to 300 volts per volt. The sound coming from the speaker must also be clear, with little to no distortion or noise present. The amplifier was first simulated and constructed through PSpice in two stages, as mentioned before, and these stages, once again, are the preamp and the power stage. The first of these two items that will be covered in this presentation is the preamplifier. The goal of the preamplifier is to prepare the input sine wave, which will be from a function generator, or from the smart device that will be connected to the circuit for amplification. Preamplifiers are used to boost the strength of the signal, which is the gain, without degrading the signal by increasing noise or distortion. Preamps are also used to boost the volume level of the speaker, which is a feature that was taken into consideration since the speakers that will be used with our circuit have no volume control. The preamplifier, constructed on a breadboard after simulation, is shown in the picture below. The schematic for the preamplifier from PSpice is located on the previous slide. The power stage of the amplifier is the second part of the amplifier that was built. The power stage was simulated again in PSpice at first, and then built on a breadboard. The power stage is connected to the preamplifier, where the speaker is connected as the load. The schematic for the power stage is shown in the picture below. A feature that was taken into account with the power stage is the VBE multiplier. This multiplier is used to provide a voltage that can be changed between the two Darlington transistors in the circuit. The outcome of the multiplier is that the voltage here keeps the Darlingtons in an on state, which will allow more current to flow from the collector to the emitter. This helps to prevent the Darlingtons from being blown out. The circuit, in its final form, is shown below, constructed with the preamplifier in the power stage. The preamplifier is located at the top of the picture, with the power stage at the bottom of the picture. Please note the VBE multiplier is present in the power stage, with a fan connected in the circuit to keep the Darlingtons from overheating, as they generate a lot of heat. The following slide is our demonstration video with our amplifier.
You can get close enough to hear it.
After demonstrating the video, there were still plenty of improvements to be made to the circuit. Despite the sound of the speaker made it appear that we have a large gain from the recording has, in turn, amplified the sound that we had coming out of the speaker. The gain of the circuit originally was too low. To fix the gain of the amplifier, the values of the capacitors of both the preamp and power amp stages would have to be adjusted to increase the gain. Another feature that was to be added was the addition of a low-pass or a high-pass filter to filter out most of the bass distortion in the circuit. Also, we were also going to play the recommended songs to observe how the amplifier can handle both high and low frequency distortion and any effects of noise. When we returned to work on the amplifier was drawing much less of a gain than it had originally, without any attempts to modify the circuitry. Our group tweaked the capacitance, resistance, and even replaced the transistors in the circuit. The gain could not be increased, and the distortion and noise got worse. So, ultimately, the amplifier had to be rebuilt from scratch twice. After the second attempt at rebuilding the amplifier, the circuit could not work again. There are several factors to this, as one of the transistors may have been blown, a capacitor blew, or one of the Darlingtons may have melted. What also could have happened is just human error in wiring the circuit. Our group did the best we could, but unfortunately, we could not successfully rebuild the amplifier.
In order to gain a better understanding of how our circuit would have fit into a full-scale application, we are going to take a look at the process of audio amplification in a car. This particular car is a 2004 Subaru Impreza, which rally fans may recognize as the base of the 2005 World Rally Champion car that Peter Solberg drove, and the last of the big-engine rally cars. Other than its racing pedigree, this car is hiding a serious audio system which led it to earn 2 second-place trophies for audio quality and sound pressure levels over 136 decibels. Although this may not seem a relevant topic of discussion as it pertains to analog electronics, we hope that in understanding the associated issues when implemented in the real world, we as engineers can create a better product which goes beyond assumptions of idealized environments. In examining the audio systems in this vehicle, we hope to uncover some knowledge of how industry engineers approach complicated issues and how audio leaves some recorded medium and gets played for our listening pleasure. To begin with, the audio input to a car stereo is handled in much the same way as in our circuit. The input can be received from AM, FM radio, CDs, DVDs, Bluetooth, or any MP3 device. The signals are interpreted from any of the various formats they are received in and processed locally within the head unit. Typically, in a car stereo system install, the signal is amplified and filtered within the head unit and applied directly to the speakers. The graphic equalizer shown in my stereo shows how the audio frequencies can be manipulated to best suit the vehicle and its listeners. The equalizer function of a more sophisticated radio plays an important role on audio quality for several reasons. Firstly, depending on the age and taste of the listener, frequencies specifically towards the higher end of the audible spectrum need to be individually attenuated to make their perceived volume equal to the other frequencies. In addition, within the confined space of a car, certain frequencies can be amplified by standing wave resonance within the vehicle. This effect causes high or low volume levels throughout the entire audible spectrum, which can again be mitigated by equalization. The image in the lower left shows another important feature to the more avid listener, which is sonic center control, otherwise known as time correction. In a car, the most important listener is the driver, and because they are not exactly in the center of the vehicle while driving, music is perceived to be emanating from the right side. To correct this and bring the music back to the driver's center, the music on the left channels will typically be retarded to ensure that both the left and right audio reaches the listener at the same time. This, in effect, creates a proper soundstage in which the lead vocalist appears audibly directly in front of the listener, with the other instruments to either side. Now, as I stated before, in a typical car, the speakers are driven directly by the head unit using very little power, typically 15 watts or so. To increase the precision of the music, special high-powered speakers will be placed in the vehicle and amplified by external power amplifiers. The main speaker types include tweeters, which play frequencies above 2 kHz, mid-bass drivers, which handle 80 to about 4 kHz, and finally subwoofers, which are driven at sub-audible frequencies of about 12 Hz to around 100 Hz. Each of these devices operating in their own particular frequency range needs to have all the other frequencies removed from its input signal. This means that a tweeter, for example, cannot play a 12 Hz signal at high power without distorting or being damaged, and must not be driven with an input signal which contains these frequencies. To address this issue, we will now discuss the means of external amplification and filtration. To begin with, we'll talk about the amplification stage, which is where we have spent the second half of our semester. This is a 400 watt Class D digital amplifier from JL Audio out of Florida. Unlike the amplifiers we have designed in our class, this amplifier uses pulse width modulation at around 240 kHz to amplify its input signal. True audiophiles will cringe at the thought of using digital amplification, but the engineer in our audience will acknowledge the fact that using digital amplification is much more efficient, which is important in a vehicle with a finite source of energy. Notice that this amplifier has very low input voltage, comparable to what we were using in our own experiment, and a very low signal-to-noise ratio, which we were striving for. All told, the mark of a successful amplifier is one which takes very little to amplify a lot without introducing noise. A party piece to note about this particular device is that it will detect and adjust for sags and supply voltage, which are very common in a vehicular application, and will compensate its internal clock frequency to protect from introducing distortion into the signal. Because we are dealing with several different kinds of speakers, the signals sent to each are tailored specifically for them. This signal filtration began at the head unit, had low or high pass introduced at the amplifier, and finally will be component specific after passing through this device. This is called a passive crossover network, and it separates the amplified signal into mid-bass and tweeter-friendly levels. This network is designed specifically for the driver combinations that I have used in my car, and sets thresholds exactly for the filters to get the most out of these speakers. In addition, if the speakers were overdriven by some enthusiastic do-it-yourselfer, the network has a light bulb to burn off excess power which could damage the speakers. Finally, this slide shows a simplified configuration of how the total speaker network is implemented. Our audio signal started at the head unit, passed through our digital amplifier, was filtered by our crossover, and finally was matched with our load to provide auditory bliss for its happy user. In conclusion, although we were unable to finalize our amplifier circuit, we did manage to build a functioning amplifier before some part of the system failed. If we had been able to restart the circuit after the demonstration video had been recorded, it would have been a simple matter to deal with the distortion in the circuit by increasing the capacitance in the preamplification stage. Although we did not get to prove our circuit, we gained a genuine understanding of how the process of amplification is realized and how to use the pieces such as feedback to better control our output waveform. In addition, we explored some of the real-life issues which face the creation of this type of system, including resonance and supply voltage fluctuations which can exist in vehicular applications. All told, this project was successful at helping us get more familiar with the different types of transistor devices and how to create circuits capable of manipulating seemingly insignificant signals.